始めたいと思います。ということで、ここのSusskindQM、SusskindQM のハッシュタグをクリックしていただき、最新というところに行くと、コンパスと、ここにもつけてます。コンパスにもつけてます。それから、ブルーキャットの方にもつけています。ツイッターの方に行けるように。で、ツイッターの方から、コンパスやブルーキャットに行けます。こうやって、あとは、こう。はい。それで、なんだっけ。なんか言おうと思って。そうそう。追いかけ再生をしてください。ちょっともう早く始めちゃっているので、例えば9時から見始めた人にとっては、追いかけ再生をしてください。それでちょっと早めの、スピードで 1.5 倍速とか2倍速で見ていただければ、私は非常にゆっくり喋っていると思うので、ちょうどいいんじゃないかと思います。それで、だんだんと時間も追いついていくので、良いのではないでしょうか。で、本はこの、サスキンドのクオンタムメカニクスを読んでます。それで、テキスト持ってない人のために、ここに、ギガファイルのところからダウンロードができます。で、このようにダウンロードして、それで今日やるところは323ページから。323ページなので、だいたい45ページぐらいいけるか。はい、323ページ。ということで、確か前回は、どんな固有エネルギーを持ってきても、波動関数は解けるんだよと、こういうふうにね、なんだっけ。If you just started at some point, actually you need 2 points. If you have 2 points for the wave function, and you can solve the Schrödinger equation by making little incremental steps, then we will almost always find that psi x grows or blows up as x becomes large, or as x becomes small or minus negatively large in any way. So if you can see this, if you have 2 points in psi, this is psi x and this is x, you will see this may be, most case it blow up. You can also go to negative direction and this may be blow up, or this may go down to 0, or this go down to 0. But usually it blow up again. It looks as if this go to 0, but then 0, 0, 0, 0, 0, and blow up. So for most energy, wave function blows up for x go to plus minus infinity. So that's a problem. Only very rarely will we find a normalizable solution. In fact, for most values of E, including all the complex numbers, solution of equation 1014 grow exponentially as x approaches infinity or minus infinity or both. This type of solution makes no physical sense. it tells us that there is an overwhelming probability that the oscillator coordinate is infinitely far away. Clearly, we want to impose some condition that get rid of such solutions. So let's impose such condition. Physical solution of the Schrödinger equation must be normalizable. This is a very powerful constraint. In fact, for almost all value of E, there are no normalizable solutions. But for certain very special value of E, such solutions do exist, and we will find them. Section 10.5, the ground state. What is the lowest possible energy level for a harmonic oscillator? In classical physics, the energy can never be negative because the Hamiltonian has an x squared term and a p squared term. To minimize energy, we just set p and x equal to 0, but in quantum mechanics, that's asking too much. Okay, asking p and x to be equal to 0 is too much. It is saying asking both p and x go to 0 is too much in quantum mechanics. The uncertainty principle says that you can't set both x and p equal to 0. The best you can do is find a compromise state in which x and p are not too spread out. Because you have to compromise, the lowest possible energy will not be 0. Neither p squared nor x squared will be 0. Because the operators x squared and p squared can have only positive eigenvalues, the harmonic oscillator has no negative energy levels, and in fact it has no state with 0 energy either. If all the energy levels of a system must be positive, there must be a lowest allowable energy and a wave function to go with it. This lowest energy level is called a ground state and is denoted by psi 0x. Keep in mind that the subscript 0 does not mean that energy is 0. It means that it is the lowest allowable energy. There is a very useful mathematical theorem that helps identify the ground state. We won't prove it here, but it is very simple to state. The ground state wave function for any potential has no zeros and is the only energy eigenstate that has no nodes. Has no zeros and has no nodes. This is same thing. This are same thing, I would say. Ground state wave function for any potential has no zeros and it's the only energy eigenstate that has no zeros. I think 0 and node, same thing. So, all we have to do to find the ground state of a harmonic oscillator is to find nodeless solution for some value of E. It doesn't matter how we find it. We can use mathematical tricks, or we can make guesses, or we can just ask the professor. Let's use the latter method. I'll play the role of the professor. Harmonic oscillator ground state. Okay, if you can say, if this is the eigenstate of the Schrödinger equation, okay, so then you can see easily this has no nodes. So all you have to show is this is the eigenstate of Schrödinger's equation. Then from the theorem we just introduced, you can immediately say that this state is ground state because this has no nodes. Here is the function that works. Psi x equal exponential minus omega divided by 2h bar. Omega divided by 2h bar. Okay, x squared. This function is shown schematically in figure 10.1. As you can see, it's concentrated near the origin, where we expect the lowest energy state to be concentrated. As you can see, it is concentrated near the origin, where we expect the lowest energy state. Where means near the origin. Near the origin, we expect the lowest energy state to be concentrated near the origin. As we expect this wave function is concentrated near the origin. It goes to zero very quickly as it moves away from the origin. So the integral of the probability density is finite. And importantly, it has no nodes, so it has a chance of being our ground state. Let's see if we can figure out how the Hamiltonian does, what the Hamiltonian does to this function. The first term of the Hamiltonian, the left side of equation 1014, tells us to apply the operator. See, I think our Hamiltonian is something like this. I think it's simplified. Simplified Hamiltonian is 1/2. Let's see. This is something like this, right? And this P is I h bar over I del x square. So this what we will see what this first term will do to wave function. So this one, minus h bar square over 2 partial square partial x square to psi x. Let's calculate that term, one derivative at a time. The first step is partial psi partial x is minus omega divided by 2h bar times 2x times exponential minus omega divided by 2h bar times x square, which simplifies to, and you can simplify by cancelling 2. Yeah. So what's remaining? What is remaining is this. When we take the second derivative, there will be 2 terms because of that product rule. Product rule is if you have this is just take derivative of the first and leave as it is the latter half. That's this. You take a derivative of x with respect to x and leave the remaining as it is. That's the first term. Okay. Then second term, you take derivative of the latter, this part, and leave x as it is. So you put x here. So this is like x times x. So first x is from doing nothing, and second x is from taking derivative of remaining part. Okay, so then if you combine, you can combine 2x to make x squared. Let's plug this result back into equation 1014 and at the same time replace psi on the right hand side with our guess. Exponential to the power minus omega divided by 2h bar x squared. Okay, so this one, this guy, you have to multiply minus 1/2 h bar square times this guy is here, and plus 1/2 omega square x square. Okay, then you have wave function exponential minus 2h bar omega square. I don't know if this is square. This shouldn't be square, right? This is not square. So this is not square. This is typo. X square. So that's the left, this one. Then right hand side we have eigenvalue E. Then we have wave function. Then we can see these are cancelled. These cancel each other. After cancelling the terms proportional to x squared exponential minus omega divided by 2h bar x squared, we discover the remarkable fact that solving the Schrödinger equation just reduces to solving this one, this equation. And you can solve Let's cancel this part. So energy equal 1/2 h bar omega. That's the result. As you can see that the only way we can solve this equation is to set the energy E equal to 1/2 h bar omega. In other words, we've found not only the wave function but also the value of the ground state energy. We found the wave function by asking. We found the wave function by asking the professor. And we found the ground state energy by solving Schrödinger equation. Then the answer is this. This is the ground state energy. The ground state wave function, meanwhile, is just a Gaussian function the professor gave us. Psi 0x is exponential minus omega divided by 2h bar x squared. He is a clever fellow, that professor. Okay, section 10.6, creation and annihilation operators. This is very difficult to pronounce, I think. Over the course of these lectures, we have seen two ways of thinking about quantum mechanics. They go all the way back to Heisenberg and Schrödinger. Heisenberg liked algebra, matrix, and had he known what to call them, linear operators. This is, I don't know. Does this mean even if is this right? I don't know. Had he known, even if he didn't know what to call them? I don't understand this part of the sentence anyway. Schrödinger, by contrast, thought in terms of wave functions and wave equations. The Schrödinger equation being one famous example. Of course, the two ways of thinking are not contradictory. Functions form a vector space. Functions form a vector space and derivatives are operators. So far, in our study of the harmonic oscillator, we have focused on functions and differential equations. But the more powerful tool in many cases, particularly for the harmonic oscillator, is the operator method. It reduces the entire study of wave functions and wave equations to a very small number of algebraic tricks, which almost always involve the commutation relations. In fact, whenever you see a pair of operators, my advice is to figure out their commutator. If the commutator is a new operator that you haven't seen before, find its commutator with the original pair. That's when the fun happens. If the commutator is a new operator that you haven't seen before, find its commutator with the original pair. What does it mean? If the commutator is a new operator that you haven't seen before. I have to say, don't worry. This word. Don't worry. Obviously, this advice can lead to an unending chain of boring computations. But once in a while, you may get lucky and find a set of operators that close under commutation. I don't understand. If the commutator is a new operator that you haven't seen before, find its commutator with the original pair. I don't know. Okay, if you have original pair like AB, then we consider A commutator operator AB, and if you find this is something C, which we haven't seen before, then try to consider commutator of C with A, for example, or consider a commutator of C with B. Some way you will have a closed form. So if you get something like C, or if you get something like A, here if you get C, or if you get B or something, then you may be able to find some algebraic relation between operators. Is that what he's saying? Find a set of operators that close under commutation. Whenever that happens, you are in business. As we will see, operator methods have tremendous power. Now let's apply this approach to our harmonic oscillator. We begin with the Hamiltonian expressed in terms of operators P and X. H is P squared plus omega squared X squared divided by 2. To figure out the rest of the energy levels, we will use some tricks. Okay, we found ground state energy. We found E0 is 1/2 h per omega. Then we will have to find the rest of energy level, which is E1, E2, E3, So in order to find these other energy levels, we use some tricks. The idea is to cleverly use the properties of X and P operators, in particular, the commutation relation XP equal IH. We cleverly use the property of X and P, in particular, the property of commutation relation X, P equal IH bar to construct two new operators called creation and annihilation operators. When a creation operator acts on an energy eigenvector or eigenfunctions, it produces a new eigenvector that has the next higher energy level. An annihilation operator does just the opposite. It produces an eigenvector whose energy is one level lower than the energy of the eigenvector it started with. So roughly speaking, the thing that they create and annihilate is energy. The thing that they create and annihilate is energy. They are also called raising. Raising and lowering operators. But remember, operators act on state vectors, not on systems. You see, operator act on state vectors. Operator does not act on systems. To see how these operators work, let's rewrite the Hamiltonian in the form. It's just the same. 1/2 p squared plus omega squared x squared. This is a classical as well as a quantum mechanical Hamiltonian, and it would be just as correct to use the lowercase symbols p and x. However, we are using boldface p and x because we plan to focus on the quantum mechanical Hamiltonian. I don't know. We don't do this. This is a classical as well as quantum mechanical Hamiltonian. So if we use lowercase, this is a classical Hamiltonian. But we use boldface p and x because we plan to focus on quantum mechanical Hamiltonian. Okay. Let's start by doing a manipulation that is correct for classical physics, but will require some modification for quantum mechanics. In the parentheses above, we have a sum of squares using a formula a squared plus b squared is a plus ib times a minus ib. It seems that we can rewrite the Hamiltonian as h equal 1/2 p plus I omega x times p minus I omega x. And actually, this is almost correct. But why almost? Why almost? The reason, because quantum mechanical p and x do not commute, and we need to be careful about the order of operation. Okay, so this is like this: p squared plus minus, p square plus, okay, p minus I omega x plus I omega x p plus I omega x minus I omega x. Okay. Actually, this guy, it is okay to do this. It is okay to rewrite this minus I omega px plus I omega xp. And it is also okay to write this is omega square x square. But the problem is here. These two terms does not cancel each other because px is not equal to xp. If px equal xp, we can say p and x commute, but actually p and x does not commute. That means px is not equal to xp. That's why these two terms do not cancel each other. Okay, so that's why this equation 1019 is not equal to 1018. It is almost equal to 18, but not completely equal to 18. Because quantum mechanically p and x do not commute, and we need to be careful about the order of operations. Let's expand our factorized or factored expression and see how it might differ from the original Hamiltonian in 1018. Keeping careful track of the order of factors, we can expand the expression as follows. So we expand this parentheses, then we obtain this part. We obtain this one. I don't know this. This is same. Okay. So this line is just a plus. Okay. So we put this one out. So we obtain this. So look at the right hand set of parentheses in the final line. We have seen that expression before. It's a commutator of x and p. In fact, we already know its value. Its commutator xp is IH bar. So, thus, the expression for our factored Hamiltonian becomes 1/2 p square plus omega square x square minus 1/2 omega h bar. In other words, the factored expression we started out with in equation 1019 is actually smaller than the Hamiltonian by omega h bar divided by 2. To recover the actual Hamiltonian, we need to add the omega h bar divided by 2 back in. So if we put this thing, then this whole thing become H. Okay. So it's almost time. I stop here, and next time we continue from 331, page 331. Okay. So then we see this is Susskind. Then see nobody else. Is it? So today is finished. Okay, so then nobody is answering tomorrow schedule. Okay, so I will just decide myself what